Ryōiki Tenkai. The domain and range of a quadratic function where there's no c coefficient or there's no constant on the function itself. This is the second form of a quadratic function where we are going to solve for its domain and range. But the processes in solving for a domain and range, no matter what the form of quadratic function is just the same. So let's start by writing this function in terms of y. Let's make f of x as y so that we could separate it or represent it later on in a form of a graph for an illustration or a support to our analysis here. So we have y is equal to x squared plus 7x. We mentioned here there's no constant or there's no c coefficient because this is an incomplete quadratic function. And it's very important as we deal with range later. But let's start with understanding what the domain is. The domain of this function is a set of all possible values of x that can be substituted here, wherein the value of y, or the actual value of the entire function, is a real number. Now, if we're going to look at this, there are no other restrictions here. There are no presence, or we don't have here a square root of an x, or this is also without a denominator of x. So we can use here any value of x here. Let's say positive 1. 1 squared is 1, plus 7 times 1 is 7, so 8 is a real number. If we use here, let's say 1 half, the square of 1 half is 1/4. 7 times 1 half is 7 halves. In terms of 4, that's 14 fourths. So that's 15 fourths all in all, still a real number. If we're going to use here negative 2, the square of negative 2 is positive 4. 7 times negative 2 is negative 14. 4 minus 14 is negative 10, still a real number. Even if we're going to use here square root of 2, an irrational number, the square of 2 is 2, plus 7 square root of 2. All in all, it's still a real number. Hence, for a quadratic function, the domain is the set of real numbers. There are no restrictions. Or in set builder form, you could have here set of x such that x is an element of real number. Again, as mentioned, no restrictions. This is the domain of a quadratic function, no matter what the form is, as long as it's really a quadratic function. Now here comes the next part, the range of the quadratic function given here. Let's rewrite this here. Y is equal to x squared plus 7x. The range is a set of all values of y that can be solved after applying all the possible values of x on our domain. Now, it's easier for us to solve for the range for some functions if there are restrictions already signified or identified on our domain. Because once you will have a restriction, then it's easier for you to identify as well what would be the restriction for your range. But since our domain earlier is a set of all real numbers, there is another process identifying the range of a quadratic function. We are going to use here the concept of the vertex of the graph of this function. The vertex is denoted as this. The vertex is a set, of course it's a point on a graph because our graph is a parabolic graph. The vertex is determined as negative b over 2a, and you have here 4ac minus b squared over 4a. This is a point which is our vertex. The vertex is also known as the point of inflection because if we're going to have a graph later, it's the point of our graph where the graph changes its direction from either going down to going up, or from going up, reaching that vertex, and then it goes down. This value here, the y coordinate of our vertex, is important and essential in determining the range of this given quadratic function. So we simply need to solve for our values here. What would be our a, b, and c coefficients? These are the coefficients of our quadratic function. A is the coefficient of your x squared, which is 1. Okay? B is the coefficient of your x term, positive 7. And C, since there's no C there, or there's no constant, 0. Now, of course, you could always plug in all of this to solve here, so that you could get the value of y. But if you were able to forget this one here, you can simply use the value or the result here. So you have for our, and we also going to use this one because we're going to illustrate a graph of it later. So you have negative b, that's negative 7 over 2 times a, which is 1. So our value for our x, for our vertex, is negative 7 halves, or negative 3 and 1/2. Okay, now we are going to substitute this in. This is a fraction, but of course we always allow fractions as it's also part of the real numbers. To solve for our y, substitute that here. So you have the square of negative 7 halves, that's 49 fourths. Since I don't have much space here, let me just use it mentally, and please follow with me. That's 49 fourths. You will have here 7 times 7 halves. That's 7 over 1 times 7 halves. It's 49 halves. But it's negative. So we have 49 fourths minus 49 halves. Okay? LCD, we have 98. So your value for your y here is negative 49 over 4. Of course, you could always check it like this. So 4 times 1, that's your a, times 0. So this is 0, right? 7 squared is 49. Then you have negative, so negative 49. 4 times 1 is 1, so you have negative 14 over 4. Again, you can always use this. But I'm just also using this or solving for x because we're going to illustrate it later on a graph to check whether our analysis here is correct. In short, our vertex is at negative 7 halves, and you have here negative 49 fourths. Okay. Now, this value here pertains to our identified value of y, and this will comprise our range. The range now is in this manner: y such that our set of y such as y blank negative 49 fourths. Why do I mention blank? Hear this. We are going to include here a portion which is a symbol of inequality. We're going to refer it to the value of a here. Our a here is positive. Hence, we'll be using this notation. If our a here is negative, it's the other way around, and only include here equality. So again, if our a here is negative, it's less than or equal negative 49 fourths. So this is now our range. All values of y, such as y is greater than or equal to negative 49 fourths. Why is it that we have restrictions here? Because we don't include all values less than this. Why is it that we have restrictions here when in fact our identified domain doesn't have any restriction? This is because we have a quadratic function where we take the power of 2 of our value of x, meaning we're solving or we're squaring it. Hence, there are numbers that can't be equivalent to our y. So here comes our illustration, and let's see if this is really correct. Okay, so our graph 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is a little bit shorter because 49 fourths is negative 12 and 1/4. Let us simply use by 2. Okay, this x-axis, horizontal axis is our x, this is our y. So partner with me, each grid here would be per 2. Okay, per 2, or yeah, let's have it per 2. So 2, 4, 6. So our point is at negative 7 halves. That's actually negative 3 and 1/2. So if this is 2, this is 4, 3 is somewhere here. So 3 and 1/2 is somewhere here. Okay, and that's negative 3 and 1/2, and negative 49 over 4, as mentioned, is negative 12 and 1/4. So that's 2, 4, 6, 8, 10, 12. Here is 13, so somewhere here. Okay, 1/4. This is now the point of our graph where the graph changes direction. This is the vertex. Okay, this is our vertex. Now, to show the correct form of a graph for our quadratic function because it's a parabola, let us use other values here. Let us use integers if it's okay with everyone. So this is negative 3 and 1/2. Let's use here negative on the other side. So we have negative 5 and negative 4. If x is, let me somewhere move it here because it doesn't have much space. X negative 5. Okay. X is negative 1, negative 4. Negative 3 and 1/2. So we have here x is negative 3 and x is negative 2. Let's try to solve for the values of x, as we need at least 5 points for a quadratic function to be graphed a little bit more appropriate. So negative 5, the square of negative 5 is 25. I have here 7 times negative 5 is negative 35. So 25 minus 35 is negative 10. That's y equals negative 10. Take note that our graph is already per grid is 2 because we adjusted it. If x is negative 4, negative 4 here is positive 16. 7 times negative 4 is negative 28. So positive 16. Negative 28 is negative 12. Am I right? Let me check again. For 25, 25, 35. For 4 is 16 plus 28. So you have here y is equal to negative 12. That's correct. For negative 3, negative square of negative 3 is 9. 7 times negative 3 is negative 21. 9 minus 21. So y is negative 12. And if it's negative 2, square of negative 2 is 4. 7 times negative 2 is negative 14. 4 minus 14, so y is negative 10. Here comes the graph. Negative 5, so 2, 4, 6, as mentioned, were 2 grids. So negative 5 is here. And negative 10, 2, 4, 6, 8, 10. So we have here, this is our second point. Negative 4 is here. And negative 12, 2, 4, 6, 8, 10, 12. Somewhere here. Okay. Next, for negative 2, 3. 3 is somewhere here. Okay, pardon, my graph is a little bit, my vertex rather, because 2, 4, 3, and 1/2. So somewhere here, this should be the vertex here. Pardon with that. Let me color this black so that it will return to its original form earlier. Yeah, just like that. Let's continue. For negative 3, somewhere in the middle, you have here 12. A little bit smaller. And for our negative 2, which is this grid here, negative 10. It's a little bit smaller because we also tried to decrease the length of our Cartesian plane because I don't have much spaces here. We're going to connect this. So we'll have this form here and something like that. And again, it will extend further, further, and further. This is the graph now. As you can see, it opens upward with our vertex here, the smallest or the lowest possible point of our graph. Now, we are doing this, we're illustrating the graph, so that if we're going to connect it with the results earlier, we can verify if our answers are correct or not. Look at our values of x going towards our left, going towards our right. As long as you will apply other values of x here and going in this direction as well, you will have infinitely many values of y as well, as this will move further up. Okay, this is why our domain earlier is a set of all real numbers. Now look at our y. Our y here, as mentioned, if we're going to apply all possible values of x in this area and even this one here, including the fractions, the y here will just be increasing its value here as well, but it will never get lower than this point. And what is this point? Our vertex. What's the value of the y of this vertex? Here. And what's that value? Negative 49/4. And why do we use greater than? Look at our graph. All the values greater than that, which also includes the vertex, but all values greater than 1,000,000, 1,010. That's why it's greater than. So looking at our illustration and the result earlier, our answers for the domain and range for a quadratic function in this given function is correct. For the next functions, Please do not forget to like this video, share this, comment down, and subscribe to our channel. This is for us to expand our domain further.